Grain dust filled the air like a deadly fog, while massive stones spun at crushing speeds, just feet from where millers worked every day. One spark, one overheated bearing, one poorly maintained millstone could turn a medieval windmill into a devastating bomb that would kill everyone inside and destroy the entire structure in seconds. What safety techniques allowed these millers to work with explosives they didn't even know were explosives? Medieval windmills weren't just clever machines for grinding grain. They were complex engineering systems that combined tremendous mechanical forces with highly explosive materials in ways that pushed medieval technology to its absolute limits. The fine grain dust that coated every surface wasn't just a nuisance, but a substance more dangerous than gunpowder when mixed with air and ignited by the smallest spark. Yet somehow, medieval millers developed safety protocols that allowed these machines to operate for centuries without the catastrophic explosions that modern safety engineers know should have been inevitable. The medieval windmill stood as one of the most sophisticated machines of its age, a towering structure that captured wind energy and transformed it into the grinding power needed to turn grain into flour. These weren't simple devices, but complex mechanical systems that required constant attention and maintenance to prevent the kind of failures that could kill operators and destroy entire buildings. The sight of a windmill's great sails turning slowly in the breeze disguised the dangerous reality inside, where tons of stone ground against each other at high speeds while clouds of explosive dust filled the air. Inside the windmill, the working environment was unlike any other medieval workplace. The grinding chamber was dominated by massive millstones, some weighing several tons, that rotated with enough force to crush human bones as easily as grain kernels. The air was thick with flour dust that coated every surface, creating conditions that modern industrial safety experts would recognize as extremely hazardous. Every surface was slippery with accumulated dust. Every breath carried particles that could ignite without warning, and every piece of equipment operated under stresses that could cause catastrophic failures. The most dangerous aspect of windmill operation wasn't immediately obvious to medieval operators. The fine flour dust that seemed like an inevitable byproduct of grinding operations was actually a powerful explosive that could detonate with tremendous force if ignited by even the smallest spark. Medieval millers didn't understand the chemistry of dust explosions, but they developed empirical safety practices that prevented most accidents through careful attention to conditions they couldn't explain scientifically. The Guild of Millers maintained strict control over windmill construction and operation, but their regulations were driven by practical experience with accidents rather than theoretical understanding of the dangers involved. Guild rules specified construction materials, maintenance schedules, and operating procedures that were designed to prevent the failures that had caused mills to explode or catch fire in the past. Master millers were required to maintain detailed records of accidents and equipment failures, creating a knowledge base that helped prevent similar incidents in other mills. Apprenticeship in the milling trade required extensive education about the mechanical systems that powered windmills and the safety procedures that kept them operating without catastrophic failures. Apprentices learned to recognize the subtle signs that indicated equipment problems before they became dangerous, to maintain the precise tolerances that kept millstones operating safely, and to monitor the environmental conditions that could turn routine operations into deadly situations. The guild also controlled access to the specialized knowledge required for windmill construction and maintenance. Master millers understood the engineering principles that determined safe operating speeds, the materials that would resist wear while minimizing spark generation, and the maintenance techniques that would prevent the equipment failures that had destroyed other mills. This knowledge was passed down through generations of careful training and was considered so valuable that guild members were forbidden from sharing it with outsiders. The construction of medieval windmills required engineering expertise that combined practical mechanics with empirical safety knowledge gained through bitter experience with accidents. The entire structure had to be designed to contain tremendous forces while providing adequate ventilation to prevent dangerous accumulations of explosive dust. The tower had to be strong enough to support massive grinding stones while flexible enough to absorb the vibrations that could shake the structure apart over time. The windmill sails represented one of the most critical safety systems, since their design determined how much power would be transmitted to the grinding stones under different wind conditions. Sails that were too large could overspeed the millstones, creating dangerous heat and sparks, while sails that were too small wouldn't provide adequate power for efficient operation. Master millwrights developed techniques for calculating sail dimensions that would provide optimal performance while maintaining safe operating conditions. The gearing systems that transmitted power from the wind-driven sails to the grinding stones required precision manufacturing that approached the limits of medieval metalworking capabilities. These gears had to operate smoothly under tremendous loads while minimizing friction that could generate the sparks that would ignite flour dust explosions. The materials, lubricants, and maintenance procedures used for these systems were carefully chosen to prevent the equipment failures that had caused accidents in other mills. But the most critical component was the millstones themselves, massive circular stones that had to be perfectly balanced and precisely aligned to grind grain effectively while operating safely. The upper stone, called the runner, rotated above the stationary lower stone, called the bedstone, with clearances measured in fractions of inches. If the stones came into direct contact, the friction would generate sparks that could ignite dust explosions with devastating results. The selection and preparation of millstones required expertise that bordered on geological science. Not every type of stone was suitable for grinding operations, and even good stones could be ruined by improper preparation or installation. Master millers understood which quarries produced stones with the right hardness, porosity, and grain structure to provide efficient grinding while minimizing spark generation during normal operation. The dressing of millstones, the process of cutting precise grooves that would help move grain through the grinding surfaces, was one of the most specialized skills in medieval craftsmanship. These grooves had to be cut to exact specifications that would ensure proper grain flow while preventing the buildup of flour dust that could create explosive conditions. The patterns varied depending on the type of grain being processed, and master millers maintained sets of specialized tools for creating and maintaining these critical surface features. The maintenance of proper clearance between millstones required constant attention and adjustment. As the stones wore during operation, too much clearance and the grain wouldn't be ground properly. Too little and the stones might touch, generating sparks that could cause explosions. Experienced millers could judge proper stone clearance by the sound and feel of the operating mill, making tiny adjustments that maintained optimal performance while preventing dangerous conditions. The environmental conditions inside operating windmills created safety challenges that required constant vigilance and specialized techniques. The flour dust that accumulated on every surface had to be managed carefully to prevent dangerous concentrations that could explode if ignited. This wasn't simply a matter of cleaning, but of understanding how air currents, humidity, and static electricity affected dust behavior in ways that could turn routine operations into deadly situations. Ventilation systems in medieval windmills were designed to provide adequate air circulation without creating drafts that could stir up dangerous dust clouds. Too little ventilation and dust would accumulate to explosive levels. Too much, and the resulting air currents could create static electricity that would ignite the dust they were supposed to disperse. Master millers learned to balance these competing requirements through careful attention to wind direction, door and window positions, and the timing of different mill operations. The control of static electricity, though not understood scientifically, was managed through empirical techniques that prevented the sparks that could trigger dust explosions. Millers avoided wearing certain types of clothing that generated static, used specific materials for tools and equipment that wouldn't create sparks, and followed procedures that minimized the buildup of electrical charges during mill operations. Fire prevention in windmills required understanding of combustion principles that wouldn't be formally explained for centuries. Yet medieval millers developed practical techniques that prevented most fires through careful attention to conditions they couldn't explain theoretically. Every potential ignition source had to be identified and controlled, from the friction points in mechanical systems to the static electricity generated by moving grain and flour. The lubrication of mill machinery was a critical safety function that required specialized knowledge about materials that would reduce friction while not creating fire hazards themselves. Animal fats, plant oils, and mineral substances were used in specific combinations that would keep machinery operating smoothly while minimizing the heat generation that could ignite flour dust. The timing and methods of lubrication were carefully controlled to prevent over-application that could create additional fire hazards. The monitoring of machinery temperatures was done through tactile and auditory methods that allowed experienced millers to detect overheating before it became dangerous. They could feel temperature changes through vibrations in the mill structure, hear subtle changes in machinery sounds that indicated developing problems, and observe visual cues that warned of impending equipment failures. Emergency procedures for dealing with fires or equipment failures had to be executed quickly and correctly to prevent disasters that could kill everyone in the mill and destroy the entire structure. Millers practiced rapid shutdown procedures that could stop the machinery safely, even under emergency conditions, and they maintained firefighting equipment specifically designed for flour dust fires that would spread rapidly through conventional methods. The social implications of windmill safety extended far beyond the individual operators to entire communities that depended on these facilities for their food supply. A mill explosion didn't just kill the miller and destroy equipment, but could eliminate the grain processing capacity that kept local populations fed. This community dependence created pressure for safety standards that protected both the operators and the vital services they provided. The legal framework surrounding windmill operations included liability provisions that held millers responsible for accidents caused by negligent maintenance or unsafe operating practices. Guild regulations established minimum safety standards, but individual millers faced personal financial responsibility for damages caused by preventable accidents. This legal structure encouraged conservative operating practices that prioritized safety over maximum production efficiency. The insurance systems that protected windmill investments were among the most sophisticated risk management tools available in medieval commerce. Millers and mill owners could purchase coverage that would compensate for losses caused by accidents, but these policies included detailed requirements for safety equipment and operating procedures that had to be maintained to keep coverage valid. The economics of windmill safety required balancing the costs of prevention measures against the risks of catastrophic losses that could destroy both equipment and businesses. Safety equipment and procedures reduced short-term profitability, but provided protection against losses that could bankrupt mill operators overnight. Successful millers learned to calculate these trade-offs and invest appropriately in prevention measures that would protect their long-term viability. The seasonal rhythms of windmill operation created varying safety challenges that required different approaches throughout the year. Harvest seasons brought intense periods of operation when mills ran continuously to process large volumes of grain, creating extended exposure to accident risks. Winter operations required dealing with ice and snow that could affect machinery operation and create new safety hazards. Maintenance scheduling had to balance the need for regular equipment inspection and repair against the continuous demand for grain processing services. Major maintenance work could only be done during brief periods when mills could be shut down completely, requiring careful planning to ensure that critical safety systems remained functional during peak operating periods. Weather conditions affected both mill operation and safety in complex ways that required constant attention and adjustment. High winds could overspeed the machinery, creating dangerous operating conditions, while calm periods might require manual assistance to maintain adequate grinding capacity. Rain and snow created moisture problems that affected both grain quality and the explosive potential of flour dust accumulation. The tools and equipment used for windmill maintenance represented some of the most specialized implements in medieval craftsmanship, designed specifically for the unique requirements of keeping these complex machines operating safely. Stone picks and hammers for dressing millstones had to be made from materials that wouldn't create sparks when striking stone surfaces. Measuring devices had to provide the precision needed to maintain critical tolerances in machinery operating under tremendous stress. The knowledge and techniques developed by medieval millers established engineering principles that influenced mechanical design for centuries. The empirical understanding of machinery balance, vibration control, and failure prevention that these craftsmen achieved through careful observation laid foundations for mechanical engineering that weren't formally codified until the industrial age brought scientific approaches to machine design. The safety culture that evolved in medieval windmill operations created precedents for industrial risk management that continue to influence modern manufacturing and processing industries. The systematic approaches these millers developed for identifying hazards, preventing accidents, and responding to emergencies established patterns that evolved into modern safety management systems. Understanding how medieval millers kept their windmills from exploding reveals a world where practical necessity drove remarkable innovations in safety and risk management. These craftsmen developed solutions to complex engineering problems using empirical methods, creating operational systems that protected both workers and communities from dangers they couldn't fully understand scientifically. The precision and reliability of medieval windmill operations represented achievements that demonstrated sophisticated understanding of mechanical principles and safety management. The millers who perfected these techniques created food processing systems that served their communities for generations, while managing risks that modern engineers recognize as extremely challenging, even with current technology and scientific knowledge. The next time you see flour in your kitchen, or visit a restored windmill, remember the medieval millers who first mastered the art of safely harnessing wind power to process grain. They worked with explosive materials they didn't know were explosive, operated complex machinery without modern safety equipment, yet they developed safety systems so effective that many windmills operated for centuries without major accidents. Their legacy lives on not just in the mechanical principles they discovered, but in the fundamental understanding that safety requires constant vigilance, systematic procedures, and deep respect for the forces we seek to harness. If you enjoy the hidden sides of medieval life, hit subscribe and give this video a like.